Okay, so picture this. Have you ever cracked one of those instant cold packs and felt it turn freezing cold in your hands? Or maybe you've stood near a burning fire and just felt that intense heat radiating towards you. Well, those everyday real-life examples are actually perfect illustrations of a chemistry topic we call energetics. Today, we're going to break down exactly how chemical reactions handle this whole transfer of heat.
Here is our game plan for this explainer. We are going to cover the flow of heat, how bonds actually dictate temperature changes, drawing energy profile diagrams, tackling lab experiments and calculations, and then we'll wrap up with some highly specific CSEC exam tips.
All right, kicking things off with part 1, the flow of heat and the direction that energy is moving.
So there is a totally fundamental difference in how reactions handle energy flow. Exothermic reactions, well, they release heat directly out into the surroundings. Just imagine thermal energy flowing outwards. But in direct contrast, endothermic reactions absorb heat from their surroundings. They literally pull thermal energy inward.
Now, for your CSEC exams, you absolutely need to know these concrete laboratory examples. If you mix sodium hydroxide pellets with water, the temperature of the surroundings rises. The beaker actually gets hot to the touch. That is a classic exothermic reaction. But if you dissolve potassium nitrate in water, it absorbs heat, which causes the temperature to drop, a perfect endothermic reaction. Moving right along to section 2, bonds and temperature changes. Let's zoom in a bit and look at the microscopic level.
Think of this as the golden rule in chemistry. Breaking bonds requires an input of energy. You literally have to force things apart, which makes bond breaking an endothermic process. Conversely, when new bonds snap together and form, energy is released, making bond forming exothermic. Now, every single reaction involves both of these things happening, but the overall winner determines your final temperature change.
In the science world, we track all this heat movement using the notation delta H, which stands for enthalpy change. Because an exothermic reaction loses heat to the surroundings, its delta H is assigned a negative sign. And because an endothermic reaction gains heat, its delta H is strictly positive. You really must remember to always include that sign.
Which brings us to section 3, energy profile diagrams, where we actually start visualizing this energy.
Let's walk through the 3 essential steps to drawing a flawless energy profile diagram. First, you carefully plot the starting energy content of your reactants and the final energy content of your products. Second, you draw the curve connecting them. That represents the energy barrier. And third, if there is a catalyst present, you've got to show its specific action on that curve.
This perfectly illustrates the 2 shapes your diagrams are going to take. For an exothermic change, the products end up with a lower energy content than the reactants simply because that missing energy was released as heat. For an endothermic change, the products sit at a higher energy content because they actually absorbed extra heat from the environment during the reaction.
And hey, what about that catalyst we mentioned? Well, a catalyst alters the path of the reaction by creating a lower energy barrier. Notice that it does not change the reactant or product energy levels at all. It simply lowers that peak right in the middle, making it way easier for the reaction to proceed.
All right, diving into section 4, experiments and calculations. Time to gather some data.
When you're tasked with calculating energy changes, you'll be carrying out specific lab experiments, things like reacting metals with acids or performing a volumetric analysis of a strong alkali and a strong acid. And the absolute most crucial instruction here, you must record your temperature changes carefully. That is the critical piece of data for literally all of your calculations.
When you go to plug that temperature change into your heat equation, which is Q equals mc delta T, the CSEC syllabus demands 3 very specific assumptions to make the math work out. First, you assume the density of the solution perfectly matches pure water. Second, assume the specific heat capacity is that of pure water. And third, assume negligible heat loss to the environment. Without making these 3 assumptions, your lab calculations just wouldn't hold up.
Another super vital experimental skill is the thermometric titration. So how do you find the exact endpoint? Well, you don't guess, you graph it. The endpoint is determined precisely from the intersection of the 2 lines on the temperature graph you plot. That peak intersection right there, that's your exact point of neutralization.
We are almost at the finish line. Section 5, CSEC exam tips. Let's lock this knowledge in.
Just a quick reminder. The reason we are focusing on these exact points is because the official CSEC Chemistry syllabus for energetics is very strict.
Everything we just covered, the potassium nitrate practical, those 3 exact assumptions, finding the intersection of graph lines, all of it is pulled directly from this official framework. It's always best to study exactly what they ask for.
Let's bring it all together in one master summary. For exothermic reactions, heat is released, the process is driven by bond forming, and the delta H sign is always negative. On the flip side, for endothermic reactions, heat is absorbed, it's driven by bond breaking, and that delta H sign is strictly positive. Truly mastering these differences is going to absolutely guarantee you marks on your exam.
Okay, let's pause for a quick check to see if you've internalized this. If an experiment with water shows a temperature drop in the surroundings, is the delta H positive or negative? Think back to the flow of heat we talked about. I'll give you a second to think it over.
And the answer is a positive delta H. If the water got colder, it means the chemical reaction stole or absorbed that heat. That makes it an endothermic process, which always carries a positive delta H sign. So as you're reviewing this material today, just ask yourself, if you can visualize exactly where the thermal energy is moving, is there any energetics question that can truly trick you? Trust your logic, and you're going to do great. Thanks for joining me on this explainer.